Hello, good afternoon, good morning, or good evening, and welcome to the International Plant Breeding Seminar Series. This is our fourth seminar on a series of 6, and we're very happy to have you. Please use the chat to tell us where you're joining from. And again, we're going to take questions through the Q&A box at the end of the presentation. We have today Dr. Ashra Amele, who is going to talk about probably one of the most African crops, the African yams or Discoria. We're very excited to have Ashra, who is originally from Ethiopia, and he's the program lead, yam breeding program lead at IITA, the International Institute of Tropical Agriculture. He got his PhD from Wageningen University and Research Center, a master in India, and the bachelor in Ethiopia. He has, prior to IITA, he has worked in several positions in national and international centers. So we are looking forward to your presentation, Ashra. Welcome, and thanks so much for accepting this invitation. I'm going to stop sharing so you can start sharing, Ashra.
Okay.
I don't know if you want to turn on the camera so we can.
Okay.
There you go.
Okay. Thank you, Carlos, for this invitation. And then I will try to share our experience with yam breeding. So my title of my talk is Operational Excellence and Customer Focus in yam Dioscorea species breeding for Africa. I'm Asrat Asfamil, yam breeder based in Abuja, Nigeria, and working for the International Institute for Tropical Agriculture. So in talk, I try to touch the yam crop and its potential, the domestication, the dispersal mechanism, some challenge of yam in terms of cultivation and the breeding and flowering and flower sex in yam. So the yam breeding goals and targets and the breeding design, specifically on the customer focus, and then our operational excellence, including the cross-compatibility, cross-optimization, and tracking genetic gain, and the last, the data management. So the yam crop is the herbaceous monocot. A vine crop that belongs to the family Dioscoreaceae. It's a perennial climbing plant that produces annual stem or vine, and it's produced underground tubers and also the aerial bulbils. It has both edible and also poisonous species. There's over 600 species. Out of this, around 11 are economically important. And most importantly, the Dioscorea rotundata, the white Guinea yam, and the alata are the most dominant cultivated and planted yam species globally. And Dioscorea rotundata is the dominant one in Africa. So in time of also at the family, and also some people also harvest the wild yams, and about 50 have been edible, I think, used in the shortage of food. So it's a generally moist lowland crop, rich in carbohydrates. And in terms of the FOA data, it's about 8 million hectares of land, and more than 55 countries grow yam, and over 75 million metric tons. So the yam holds a good food and also traditional medicine value. And it's important in terms of the global food security, but it is understudied or underutilized orphan crop. When you see the distribution of yam production globally, it's more in Africa and some part of in Brazil and Central America. And we can have also some production in Japan and in the Oceania regions. So when it comes to the production, about 97% of the yam production is coming from Africa, And from the Africa, over, I think from 20 to 20 years of the average, Nigeria, Cote d'Ivoire, Ghana, Benin, and the Togo are the major producers. So this is the yam production, the yam belt, where you can see about 8.5 million tons, or about 1 million hectares of land, and about 70 million tons production occurs. And even though the yam production is about 40% of the cassava, it has a value of about $40 billion, which exceeds all the other African staple crops. And it's also support the livelihoods of over 300 million people in Africa. Not only the staple food, but it's also very important in terms of a culture being involved in many life ceremonies in Africa. So the main area, the yam production area, is around here, and you can see in terms of the total area, there is more of Nigeria, the higher producers, and the total production. But when it comes to the productivity per unit area, it's a bit low, and the highest is about 20 to 24, where we can see from in Ghana. But the highest producing Nigeria, it has lower productivity per unit area. So when we see the domestication and dispersal dynamics of yam, I think initially it is around Asia, and then it moved to the north. And from the north, then the early Oligocene and late Miocene regions to move to downward. And this is the present day, the yam species is some part of Nile and then some Caribbean areas. But for the most important yam species, we call it the white skinny yam, its domestication history shows that it's from the Dioscorea absinica, which is savanna adapted wild yam, and Praensilus, which is the rainforest adapted. And then I think the two cross gave the Dioscorea rotundata. And again, Dioscorea rotundata cross with Dioscorea bulkiana gave Dioscorea cainensis, is one of also the species in Africa. And then Dioscorea rotundata cross back to Dioscorea togonensis that gave the triploids yam. So when you can see here from down, this is the Praensilus wild species, well as the yellow one or the brownish here is about the savanna adapted absinica, and this is the proposed domestications, hypothesized domestications, and origin of for the Dioscorea rotundatas per some of the studies. But when it's the second, which is globally most also dominant, is Alata, which we call the white or greater yam. It's the study shows it has 2 independent domestication centers in Southeast Asia, and then there's hypothesis move to Africa, to West Africa, and then move to the America. The major challenge of yam in terms of cultivation is some low-yielding cultivars, the clonal degeneration, disease, pest, including the virus, fungus, and nematodes. And it has high production cost. As you can see from here, you have to create a big mound to produce yam. And yam has been cultivated in Africa, especially with fallow system of minimum 5 years. But because of the reduction in the fallow system, the soil decline, soil fertility decline is one of a problem. And in general, it has underdeveloped agronomy and seed system. And in terms of seeds, over 30 to 40% of the produce is used as a seed. So a huge amount from the cultivation we used as seed, and it has generally high post-harvest loss, and some with the recent climate change related to drought and heat stress, because now moving from the forest region to the savanna region and suffering from the drought and heat stress. But for the breeding program, it is multiple species. So far we have about 11 economically important traits. Is the multiploidy, 2N, 2X up to 40, 3X at 60 and 80, some of the dominant species. And flowering is very complex, is sometimes shy in flowering, and then flowering synchronization is a problem. Pollen viability and the stigma receptability are some of the impact for the hybridization success in yam. And it's a lengthy crop, and it's also climbing growth habits that make the crop, especially for the breeding difficult, for testing difficult, need support. And most importantly, the high phenotypic plasticity, intraplant variability is very high, that reducing accuracy in the breeding and phenotyping trials. And generally, both for the cultivation as well as the breeding program, is low multiplication ratio for obtaining uniform planting material to conduct the breeding scale at breeding trials at scale. And in general, there's limited breeding and seed technology and capacity of research delivery compared to the other crops. So when you see the flowering in yam, it's dioecious and sometimes also monoecious, but this you can see the Guinea yam, the female flower. This is the male flower, and this is the monoecious, and this is the fruit. So sometimes it's not flower at all. But the sex determination system in yam, there are some species that's XY or XZ system, but a crop, Tamru et al. In 2017 determined that it has ZW system, being Alata also X or Y system. So it's like ZZ is male, and when the female, because of this expression at Z locus, it can suppress the W locus can suppress the expression of Z locus and become a female. And when it is not expressed, it become a male plant. So this is how the hypothesis about the mechanism of sex determination in Guinea yam. And through the bulk segregant sequencing, is some markers identified that is located in the W region. And there was a marker which is amplified with the female, but which is not amplified in the breeding population, and it can also predict about like 68% of the material male female. But because the female is, it can be also female, it can be also male, because both monoecious and then the female are genotypically the same. So, but when it comes to the expression, that become a problem for this type of a system to correctly predict the materials. So when you can see from here, it's this graph showing using a markers, yeah, we can clearly make the male and the female genotype, but when we see the phenotype, we have different types that include male, female, monoecious, female, monoecious, female, male, and also flowering. And generally even in gene bank accessions, we see large majority of the plants are not flowering, but in terms of the phenotype, males are higher than the female. That's one of the challenges also in the breeding program. So our goal in the breeding program is to develop resilient and high yielding yam variety that meet the end users' needs. We focus on high and stable tuber yield, resilience to the biotic stress, and better food quality, especially for the processed and the fresh tuber market, and suitability for the wear and the seed yam production. And the landscape of the yam breeding targets, the Yam Breeding International ITS started in 1970s. It gradually added new traits with primary focus on the yield, dry matter, and resistance to the disease, anthracnose virus, and the nematode, and the tuber characteristics that are cherished by consumers, like size, shape, and the culinary quality. And also the plant architecture, they're looking for those plants which are less tendency to depend on the staking. And very recently, we are also focusing very much on quality, that is for the tuber flesh color, oxidation, starch property, and the sugar contents. But generally, we have some missing traits in advanced breeding lines, and they also release cultivars, including the high level of resistance genes for virus and anthracnose nematode. And we have also the problem with getting shrub-like or dwarf plant architecture and early maturity tuber bulking, and it's underground tuber, so it's susceptible for deformation because of the soil compaction. And that also cause some problem in terms of quality. So these are some of the areas which have some missing traits, and some low tolerance to low soil fertility are some of our missing traits in our breeding target. But when we see the improved varieties and also the farmers popular varieties with this the metabolomics analysis, the metabolite profile, and then all the improved varieties clustered at one side as compared to the farmers popular or landrace varieties. And we also see there's low adoption rate of the improved varieties, might be that not been exposed to the farmers, or these improved varieties are not meet the farmers need. But from this analysis, we found that farmers varieties are comprised, or the traditional varieties comprise a great level of many amino acids around here, sugar and phosphates, while the improved variety contains high level of abundant citric acid, malonic acid, and some announced around this area. So this shows that the improved varieties are more so because of citric acid and the mastic, the ethanolamine and the malonic acid, than the sweeter farmers varieties. So I think this generally shows us, and from the breeding program, maybe much emphasis has been given for the some level of resistance to some disease compared to the consumer acceptability. So with this, we try to focus much more on the consumer acceptability, and then how to improve our operational excellence in order to drive the success. So that means we are in the program design, we are thinking to from researcher-based design, where that's the breeder things that need to be solved, to the user-led design, where the program, what problem does the YAM user consumer need to be solved. So there's a shift from researcher-based design to user-led design. And then breeding process, we have also involved the action steps to change the genetics of the plant from the present level of performance to and productivity to the reach target, then how to make it faster, to make it accurate or more productive, so that it can continuously deliver superior varieties, and of course the process to make it more cost effective. So our major focus is aligning product concept to the breeding objectives. Then we have 3 questions we ask: who are our target customers, their size and their diversity, and their location or the ecology, and what they are looking for, especially the description that give that guidance needed to the design, needed to design the breeding pipeline and acquire the needed trait for the client. So the needs and the requirements, and also their values, and then what's our reference for you. So in this process, I think the passion and the commitment to serve the customer, and provided that different clients in the YAM value chain have different requirements. So in order to frame all this and then put into a breeding design, then we looked at the generic YAM production stage value chain in the actors. So it includes from land clearing, land preparation, planting, staking, fertilizing, and also harvesting. So it's a lot of people are also actors are involved, including us from the international institutions. There are also national research institutes, farmers, extension, agro dealers, and then transporters, middlemen, because YAM is also used as for the wholesale as a national retail market. Also it's exported targeting the African diaspora in US and Europe for the global, and finally the national and the global consumers. So all these different actors on the value chain, they have needs and the requirement, and then we have to come up with the set of traits for the product that meets the market or the client needs in the value chain. So in YAM has many characteristics, And variety is a construct of traits of different value. But in our program, we have over 180 traits in YAM ontology. So we are just questioning ourselves, do we want all to improve them all? There are many to improve and then many to record. So the issue is not all traits are economically important, or not all traits are equally heritable. There is also some correlation between traits. So then what we want to, where we want to go in terms of our breeding goal. So the value of improving different traits and then combining different information on different traits, and then what really we want to deliver to the client in terms of improving productivity, improving the quality or the resilience. So having all these, we come up with a trait typology in the breeding program. So when we see the trait typology, we have those that are measured but no value by themselves. We have large majority of traits, but they have some traits that have value but not measured. Still, there are many. So when we see the measured traits versus the breeding objective selection traits, we just want to look at around at the middle where those traits which are measured and which have the value. So in order to come up with this, we try to see what are the set of traits that the end users are looking for. And then the survey was done with farmers involving in Nigeria and Ghana. Here you can see that there is a list of traits the farmers mentioned, but it is a wave. Some users are, okay, this is the traits I'm looking in the varieties, which is very important, but for some it is not important. When you ask them to prioritize, some rank first, the other rank fourth or fifth, or some say it's not important in my top ranking. So this also make a complex in order to address how to use all this information to come up with a clear set of traits that the end user targets. I think the other one is the same exercise we did in Ghana. So with all this, we come up with the product concept, where in the product concept still there are two approaches. The one is providing the best option approach, where that means giving the best choice, to develop a list of attributes that target clients or market consider when adopting or rejecting a new variety. That means focusing on few traits and then maybe ensuring some other 50 or 20 in a range fall within the acceptable range. So that means there is no finite time horizon for such kind of product concept. The other one, where now from the CG now we are focusing, is the replacement approach, providing a comparable alternative, identify the market leading variety for replacement, those the one I mentioned before, the leading cultivars, and in the target region, and describe some traits variety in the region. So that means we need to also identify what's farmers or consumers like about those varieties and what they dislike about those varieties, and then compile all this information and come up with the expected new variety in order to replace this. So that means we are just developing a product profile or specification for the new varieties. So in this process of defining a product for the client, we have a set of traits a new variety must have to successfully replace the existing ones. Those are high demand but low potential. And they are also include some traits that differentiate the new variety from the existing one, both high demand and high potential. So with all this analysis, we come up with 3 product profiles. I think it's maybe just to show you this, we are using as a benchmark for different traits we have identified, where the red means when we are doing our advancement decisions, any material which are falling for the particular red will not consider it, but we also have for each of the traits that make the product profile. For instance, this one is for the early maturing, less likely to depend on staking white yam, where we target at Guinea Savannah, and the market is for domestic whole tuber consumption or premium exports, both processed and also for the fresh whole tuber consumption. So this we are used as a guideline. So we have now the targets where those products and who need our products and what are the threats we are addressing our breeding program. So we developed this type of product profiles for the other white yam category and also for the water yam category. For the water yam, especially Bealata, because we are working with 2 species. So anthracnose resistance is our main concern on top of the adaptation and as well as the yield and also the quality traits. When it comes to the quality, the shape, appearance, the tuber color, and also the oxidation, pillows, and boiled and pounded yam quality, all in product profile, because we are giving more emphasis on the efficiency for the production. So the main challenge is the attribute the target client or market consider when adopting or rejecting a variety is not well known. If it is known, exists, it's maybe context specific and also diverse. And we have also a lack of information on the market volume and the boundaries. And then the scheme for testing the product to market acceptability is not well developed, especially institutionally when it comes to our national partners. And we have also the lack of a system for the feedback on the market needs, so that that can be used to adjust the breeding program targets and the goals. And most importantly, this kind of exercise is we are get from the qualitative information. So translating this qualitative market preference and quantitative screening tools for return application and breeding program is lacking. And having this, we have also looked at is how we can also improve our genetic gain in the breeding program. So in yam is a 2-step process, the breeding, that involves both sexual and asexual reproduction. So we have both the population improvement and also the variety development section. In population improvement, we focus very much on the parent selection and the pollination, and the variety development, clone selection, and then the variety replacement. This is the basic, the baseline scheme where we are using. So we have the parents, and then we get botanical seed. From botanical seed, we generate plants, from plants tubers. From tubers, then we get tuber to plant row, and where we evaluate our materials and recycle for the population improvement. Any material which is better, superior than our checks, then we advance them for the variety development. So in this process, we have to define our scheme and also understand the dimension of the breeding steps involved. So, and it is actually known that there are different schemes exist and also they are different in their efficiency. So then as a breeding program, we need to decide on the best possible scheme and how we are going to define the best possible scheme for us. Maybe experimental comparison, because the yam is lengthy crop and it may take a longer time, so that may be not possible. The other is using experience. But now we are focusing very much on some theoretical expectation that I'm using some simulation exercise. So in this process, we use the breeder equation in terms of the changing the genetics of the material from present level to the defined, to reach the defined target, and some use of some state-of-the-art techniques to reduce error and speed up selection turn. So this focus on the intensity, accuracy, and the variance, how we are maintaining the diversity in our program. For this, the program is, we are emphasizing much on the parent selection crossing plan optimization. So for the crossing, the parent selection, the compatibility, and the relatedness, breeding value, flowering, the flower sex are some of the criteria we use. And we also use both the full sieve and half sieve breeding, and also the crossing block management, and then how we can also track our selection gain in our program. So when I did the retrospective analysis for the yam crosses for the last 10 years, in our pollination success, and then factors that influence the crossing success in terms of genetic, weather, and the technician effect. So in general, in both our two species, we have on average about 21% in white yam and about 31% in water yam, the pollination success. So we try to see about what is the problem with this, and then the genetic relatedness also has contribution for the cross compatibility. But our analysis show this is for the water yam. There is no effect of the genetic distance between the parents on the cross compatibility rates using the index we are using here for in terms of the crossability rate, seed setting rate, and seed production efficiency. The same also is true for the white yam. We don't see any effect of the genetic relatedness in the cross compatibility in yam. And we also try to see the parent heterozygosity in terms of the average cross compatibility rate or percentage high crossability. So the parent heterozygosity level has also no influence on the sexes. But we noticed that the quality of the pollen germination has effect. You can see from here, even this is from 2020 trials, at different time of pollen collection and then the germination of the pollen from the less than 1 hour up to 4 to 5 hours. We see the variation in the pollen germination rate, and then we try to see the pollen germination, and then you to predict this as about the successful fruit set rates. But it shows that still it plays role, but in some cross combination here, there is no zero fruit set. That means these two are not combining very well, or there are some issue with some other factors are playing a role. So this, with this information, will go to in future consider as to what is the main cause for the cross compatibility in our affecting cross compatibility in our program. So we also looked at the weather variables. When you see the annual for the 10 years, there is no variation, that has no effect. But when we looked at for the period of the months, then the weather variability are there. So we try to see which one of the weather factors also affecting our pollination success in both rotundata and errata crossing block, and we can identify that some maximum temperature and then the relative humidity, some even including the rainfall, are playing a role in the pollination success in our crossing block. So this tells us that looking for the best crossing site or the environment, as well as the environment management, also can improve our crossing success. We also try to look at the technician you're using in the crossing block. You can definitely see some the technician skill also matters in improving our pollination success. Having this assessment, then we try to see also a simulation on the optimum number of parents to use in order to maximize our breeding program and also the recycling stage. So our baseline is we start with about 90 parents, and then at every 4 years, select new progenies from the second colonial generation, and then go back to use at 45 old good parent. And because at this stage, there's no replication, and this is how we are using. And then we try to see if we increase the accuracy, replication, and how the genetic gain looks like. So this is the baseline we are using. So not including the old parents, I think it can increase with not all the parent, but if we increase the replication of selection of new parents to 3 replication, so we can at least get a good genetic gain. If you continue with 50 clones at founder parents, without losing the genetic variability, we can continue about for 20 years. Then we also looked at the selection method for the parents, phenotypic selection, BLAP, PBLAP, GBLAP, and if we include GBLAP and some level of first clonal generation with replicator, it clearly shows that here for using the GBLAP method is advantage in terms of higher genetic gain compared to the other method. This is using base index for our 6 traits. And then we looked for each of the traits, which you can see for the average tuber weights, for the tuber yield per plant and the tuber yield per unit area, we can achieve the gain. But we see that for the dry matter, the gain is not too much. So this gives us an indication that we look for maybe in our new some source of high dry matter content the parents or breeding program to improve. But still we can manage this the virus severity score. So we are just making a gain in terms of this. So this is the simulation exercise, the one I showed before, and now we also try to see if the value of genomic prediction and tuber yield in guinea yam, and then we try to GBLAP with different methods, and it is clearly shown that the GBLAP is superior as compared to the other methods, as we have seen in our simulation exercise. So the issue now here is after this exercise, then how we can increase our accuracy of with increase the accuracy of a selection of the parents with replication. So it's for yam, if we start with one botanical seed, it may take 4 years in order to get more material for replicated trials. So that's the main challenge. And then we looked for the seed innovation technologies in order to generate more plants from the botanical seed. This is the semi-autotrophic hydroponic system that help to shorten the yam breeding cycle. So in this process, in last year, we introduced about 52 families of over 2,000 progenies. If we allow them, we are only getting 1 tuber, but we use these techniques and try to generate over 30,000 plantlets. On average, 30 plantlets per progeny. You can see here the tuber. This is how we just put the plants, and even we not go for the field, but within the screenhouse, we can get the mini tubers. So that help us to increase accuracy with replicate trials at first clonal testing, and then we can increase our cycle. Okay, so for the genomic resource, we have both ALATA, we have the reference genome for Tundata and for also Demotherium, and this is for the one of a medicinal crop in China. So we have some resource for reference genome. And in the IITA, we did a lot of genotyping using GBS, whole genome resequencing, and DART techniques. And then we use for diversity analysis for the heterotech group development in our crossing program. And also we are now moving to apply genomic prediction and the selection in the yam breeding. And from a process of pollination, if we leave very compatible plants in open pollinated, there is a potential to get more fruits, but parent pedigree construction is a big problem. So we applied markers to reconstruct their pedigree, and we successfully reconstructed the pedigree of the progenies coming from open natural pollination using some very compatible parents. That gives us an advantage for implementing half-seed breeding in yam. So, and tracking and genetic gain in the breeding program. So we use both the ERA trial for the dry matter and oxidation intensity, where we include all the release and some the elite clones being evaluated for 2 seasons. And we also use some historical data. For instance, for the historical data, both preliminary and advanced performance trials from 5 years of window. And that has been in different locations in West Africa, about 12 sites and over 258 clones. And then we use the mixed model analysis to extract the blue values and then use these blue values for regression, and then we come up with the genetic gain trend. So for instance, for fresh tuber yield, we have about 1.65 percentage, but the tuber dry matter is, we are not making progress. I think we have seen even from the simulation shows there's some challenge. But for oxidation, yes, we are making progress, because for oxidation, our score is whenever it is low means good, high means bad. And when in Alata, still the trend is, even though it's low, but for both the key 3 traits, the tuber, dry matter, oxidation. But tuber, dry matter, we are also, oxidation, we are also doing good. So we also monitor the heritability and also the gain we are making from selection from each of the advancement. So this is to show about using over 300 clones evaluated in one station. And then we use an index selection involving these 4 traits. And those based on the index, you can see the selection gain for different traits we are achieving. We also compare the selection gain in terms of the population mean, as well as also the best checks you are using in our testing. So with this process, we try to monitor the gain we are making. So I think the last one is about the predicting the variety potential in the target environment, because when we test our materials in different locations, we cannot go to each individual farmer's field, but using the site we are evaluating, and also the data from the statistical information we are getting from each of respective sites, then we extend the regression analysis to predict the yield in target environment. So through this process, you can see from some of our materials, we identified good in terms of our on-station testing and also our on-farm testing. Then we predicted for their potential for different areas if each of the farmers, if for instance here, this states the statistical yield, the data we get from the extension system is for that area is about 11 tons, but the yield from this variety is predicted about 25 tons. And then there's the confidence interval. If any the farmers around that area use it, can, I think between 25 to, it's very good confidence interval. So with this process, when we are recommending the material from our trials to the farmers, and then we use all these assessments in order to have a confidence on the materials we are recommending for the release. So the lastly, we use the data management in the yam breeding. For the yam base is our data management system we use. It's a part of the breed base. So you can see here about the proportion of material coming from the ITA and its traffic. It's around here where the planting time comes. So all the people use for designing the trial. And this is part where we have also upload our data and do some analysis. So thank you very much for your attention. And I would like to acknowledge also some our donors and also our partners who support for success of our program. Thank you for your attention.
Thank you so much, Sarat. Very comprehensive and good presentation. We already have one question. Please, if you can write down your questions in the QA. The question we have is weed management a problem in yam production? And if so, what's the value of developing herbicide-tolerant yam varieties?
Yes, I think weed is the main challenge in yam cultivation. So I think the value for I think there are many I would say the game-changing traits for yam. Yam is herbaceous vine. So converting from the vine to bushy type is one of the area we are looking forward to. We don't have some diversity for that. And the other issue is making it is herbicide tolerant is a key aspect. But because of the limitation from funding and also our capacity, we are not focusing in developing herbicide tolerant yam varieties. Maybe I think the suggestion from mutagenesis or from the other methods, it's promising. We have some trials on the using genome editing and platform. They have some proof of concept, but we have not progressed with that aspect because of the funding problem. But it is really, it's high value areas, especially for herbicide tolerance in yam and also for the changing the growth habit from the vine into maybe a bushy type less than 1 meter of vine length. That really revolutionized the yam production. When you see the yam cultivation in Africa, and our estimate is even in Nigeria about 6 million hectare, and then it's about for 1 hectare about 10,000 tubers, and 1 tuber is more than 1 naira of the which is about 0.02 something dollars. So it's a huge economy, but the seed system is not developed very well, and such kind of, and I think traits, incorporating this kind of traits in the breeding program may also contribute much to for the food security and also for the yield in the region.
So please put your questions in the QA. In the meantime, Asra, so you have wheat as a main economic challenge. You have the mounding for planting, which I imagine is also highly labor intensive. You have the staking, and I imagine the harvest of yams, because of the size of the tubers and you need to preserve integrity, is also quite labor intensive. In a time where there's more and more people moving to cities, the urbanization in Africa is considerable. What's the future of yams? I mean, if we don't move technologically, is it a crop that is destined to be consumed at Thanksgiving, like here in the United States, or is there a future if it's not technified?
Yes, I think this is an important question. So this is the area we are really discussing in order how to, especially to mechanize the yam cultivation in terms of weeds management, as well as even some adjustment in agronomy, and then looking for suitable mechanization so that yam can be grown by maybe larger farmers. So this is the area we are looking for the opportunity in order to see how we can utilize such, how we can turn that challenge as an opportunity for future growth. And you know, it's in yam, before you are using fallow, and then also now it's moving to the savanna areas, becoming an open field crop, and some little adjustment in the agronomy, and combining it with some suitable mechanization. I think that will make a big change. And in the breeding program, that's why we are focusing also developing some varieties which has less tendency for the staking needs, and also produce, you know, one of the areas we are also looking now is about resistance to soil deformity, and also for the mechanical damage, you know, maybe curing or some, we are looking also those mechanisms. And then other than going for big tuber yam, we can increase the population density and also go for some varieties of size 2 to 3 kg. So I think these are the area. And now there is also a demand from the processing They are looking for not big size, they're medium-sized yam. So I think these all factors are pushing. I think in future there will be a possibility to develop some those mechanisms, that's mechanization, and also develop some varieties for the suitable for mechanization.
Thank you, Ashraf. I have two questions that are received by phone, by WhatsApp. Which are the causes of clonal degeneration, and which are the main parameters to evaluate taste? That question comes from Colombia, by the way.
Okay, which stage?
Which are the causes of clonal degeneration that you mentioned, that the clones will degenerate, and the other ones, which are the main parameters that contribute to taste evaluation?
Oh yes, for the clonal degeneration, I think the main thing is disease, especially virus and the nematode. So because the nematodes attack the tuber, and the virus also cause the main cause for the degeneration. But we can see some of farmers' most preferred varieties are disappearing because of this problem. But there are also some varieties which are, especially for the virus, it used the recovery mechanism and they still persist in the system. But for the quality assessment, in our breeding program, we have already institutionalized, especially for the boiled and pounded yam quality, where we use consumer acceptability, starting from the preliminary evaluation. That means if I count with the clonal generation, after fourth clonal generation, we go for the quality assessment. It's basically because of we need more tubers in order to maintain also the seed, as well as also use those material for the clonal evaluation. But we go very intensive when we have the national performance test. We are pushing those material for more the testing site evaluation.
What about the use of NIRS, Ashbert?
Which one?
The use of NIRS, near infrared.
Yes, NIRS. Yes, with the RTB food project that we are getting the support from BMGF. We have the calibration is almost done. So now they are validating with our data, even from our 2020 harvesting. They are validating their calibration model. And immediately when they finalize the calibration or the validation, then I think there's high potential to use NIRS, especially for the dry matter determination and also some other attributes. And so we have also now some instruments for the texture analysis. So there are some new developments coming in order to have a high throughput phenotyping for our quality traits. But in the program, we intensively use for pounding the RVA, viscosity analysis for the starch property, because we see that qualities correlate very well with the pounding quality. So we are using some of those phenotyping methods and the tools for our breeding program.
We have another question here that if you can talk a bit about the repetitions and setup for your test plots. I think it's a very timely question since you are planting at the moment.
You mean for the efficiency?
Well, the question is, talk a bit about the repetitions, how many repetitions and the setup you have in your test plots.
Okay, yes. So I think the issue here is when we start, let me start from the crossing block, we get botanical seed, and one seed produce a small tuber, and then we plant that tuber, and then we get a bigger tuber. From that bigger tuber, we get 3 plants. That means at 3 years, we get 3 plants. So in that, the first clonal nursery, we use augmented design where we not replicate the test clones, but replicate our our standard clones. And then when we advance, we go for at least 3 replication and at least 2 location, and also increase the size of the plant from like 1, 3, 5, 10. That's the plants.
The number of plants.
Okay.
Okay.
The number of plants we use per plot. And then from single repetition to 3 repetition. And that's how we use. But when we identify some good promising materials after multi-location testing, that's the national performance trial, we go for at least 3 or 2 clones, and then we increase the plot size up to 20 and then move a single plot, but use on farms as a replication. And where we also invite the local food processor to test our materials and score for the quality. So that's how we use. But now we are also implementing the centralized facility for clonal propagation, where some vine multiplication techniques, where we can start from the very beginning with the replicated trials by producing mini tubers.
It's an interesting challenge that most vegetatively propagated crops pose for breeding.
Yes.
Question here, due to the shortening of the fallow period and the pressure to produce, to increase production in land that is not usually used for yams, what attributes are you selecting for that to enable production in you said that savanna is one of the areas where yam production is moving, isn't it?
Yes, now it's the Southern Guinea savanna is the open field where you can see more yam production is now shifting to that direction. Mm-hmm. So in that sense, what we are trying to use is we select also some of the materials under low soil fertility, and we also have a smaller trials where we identify some materials which are responding good for fertilizer application. Mm. That's, I think, the main area we are looking for, the low soil fertility tolerance.
Okay. And the last question that we have is, what are the mechanisms that that underpin tuber dormancy, and if you guys have been able to determine and control those mechanisms?
I think no, because there was some study being done by even PhD level, but it's very difficult to, and I think from that report, there is no really some mechanism in order to break dormancy or to slow dormancy. So, but now currently we don't have even any research on that area.
All right. Well, thank you so much, Ashra. We are almost at the hour. We will share the recordings in a few days, and you will be able to go back to look at those recordings, or people that has not been able to attend this seminar will be able to look at it. Again, please, you know, we show photos and music at the beginning. If you have photos that relate to your crop and to your to plant breeding, please share those photos with me. Thank you again to the help I get from Brandon, Janine, Anthony, and we'll meet next week at the same time to listen to Dr. Michel Ragot from Nouvelle France Genetics, talking about technologies for all, bringing new crops to the forefront. It's promised to be a very interesting presentation too. So I look forward to your attendance. And until then, you guys have a very good week. Thanks again, Ashra. And I hope you have a very good planting season there in Nigeria, okay? Thank you so much.
Thank you very much.
Okay. Okay. You guys have a nice day. Bye.